Hello, everyone. Welcome to the lecture 2. Lecture 2, second law of thermodynamics. Second law of thermodynamics was discovered through the investigation of the efficiency of a heat engine. There was a paper published in 1824 by Nicholas Leonard Sadi-Carnot. He discovered that the maximum efficiency of a heat engine is determined by the hot and cold temperatures of the engine. It is less than 100%. The process was studied by a Carnot cycle. It has 4 states of a system connected by 4 processes. State variables of these states are temperature, pressure, and volume. As shown in this diagram, the y-axis is pressure, x-axis is volume. The 4 process starts from this point. The first one is a constant temperature. The volume changes from V1 to V2. So it is compressed. So the surrounding doesn't work to the system. So it's positive work, but the system loses the heat to surroundings. So it's negative. The second process is here. The volume changes from V2 to V3. And the work that's from the surroundings to the system. So it's positive, but no heat. It's an adiabatic process. The third process is expansion. The volume goes from V3 to V4, but at constant temperature. So the system does work to the surroundings, but also it absorbs the heat from the surroundings. The number 4 process is adiabatic again. With the heat exchange equal to 0, the volume increases from V4 to V1. The system does work to the outside. So putting together, the system starts from here, goes with 4 internal processes, and it comes back to the original place. So based on the first law, there's no change of internal energy because the state doesn't change. But however, this 4 process has 2 heats, dq1 and dq3. One is positive, one is negative. And then the 4 work. 4 work add together, get dw. But that together equals 0 because the system returns to its original state. So the efficiency is determined by how much work does the engine do to the surroundings. Okay. Remember, the system doesn't work to the surrounding will be negative work. And the heat taken by the system for the surroundings to do the work. So that's how to define. Eta equal to minus dw divided by dq3. But the dw can be solved by this equation. Minus dw equal to dq1 plus dq3. So dq3 divided by dq3 equal to 1. So dq1 divided by dq3. Remember that dq1 is the system gives the energy to the outside is negative, and dq3 is positive, the system gets energy from the surroundings. So because one is negative, one is positive, so the efficiency of the engine is less than 1. So that's 100%. So this is called lost heat. dq1, the heat is lost to the low temperature reservoir of the surroundings. So the formulation of the second law was done by Rudolf Clausius in 1850, a bit more than 24 to 50, more than 20 years later. Based on Carnot cycle, Clausius concluded that heat can only spontaneous flow from a hot body to a cold body. So he defined an entropy change due to heat change. So if the heat is taken from the high temperature to low temperature. So the change of the entropy due to the heat change is the heat change divided by T. ds equals dq over T. So total entropy change for heat flow from a hot body to a cold body would be the entropy change at the hot body plus the change at the cold body. But however, remember that the heat is taken away from the hot body, so it's negative dq divided by Tb, that's high temperature change of the entropy. And then the when the heat is put into the low temperature body, the dq divided by Ta, as a positive, the heat is getting into the low body, cold body. So put them together, because Tb is larger than Ta, and this entropy change for that process or heat flow is positive. That means the change of the heat flow of the process of heat flow will produce entropy, the increased entropy of the system. So that becomes second law of thermodynamics. So it states that any a spontaneous internal process, IP, in a system must result in entropy production. That means that the process itself has to increase the entropy of the system. And the DIPS less than 0. So then we consider equilibrium condition. If there's no any spontaneous process, internal process possible, there is no entropy production by any process in the system. So equilibrium condition is basically DIPS equals 0 for all possible internal processes. So example is the heat from sun to earth. We know the sun has high temperature, the earth has low temperature. So if we put the sun and the earth together as a system, we consider the heat transfer from the sun to the earth. We calculate the entropy change in the sun and entropy change in the earth. So we calculate the entropy production of the system. That would be because the heat is taken from the sun. So this portion is decreasing. So it's minus dq divided by temperature of the sun. And then to the earth, the heat arrives at the earth. So the dq divided by T, the temperature of the earth. Since we know that the temperature of the sun is much, much higher than the temperature of the earth, so this process of heat transfer from the sun to the earth will increase the entropy of the system if you put this sun and earth together as a system. Thank you. Lecture 3, we're going to talk about the third law of thermodynamics.